Hi, so in this video, we're going to look at force diagrams, and in particular, Newton's first law of motion. And this states that every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. We're also going to look at a resultant force. And a resultant force is the single force obtained by combining a system of forces. So we'll begin with question A, where we have this particle and it is acted on by 4 different forces. Now you can see that the force acting to the right of 10 newtons is equal to the force acting to the left of also 10 newtons. So these two forces will cancel each other out, which means there is no resultant horizontal force. So because it is not being compelled to change its states, horizontally, this particle will remain the same. But vertically, there is a 20 Newton force pulling it downwards and a 10 Newton force pulling it upwards. So there is a net force overall of 10 Newtons pulling it down. So we have our particle, and we've got 10 Newtons net force pulling it downwards. So this is the difference between the 20 pulling it down and the 10 acting in the opposite direction. So because we've got 10 Newtons pulling it down, the motion of a particle means it will be accelerating downwards. Notice that I say accelerating, not its velocity. If its velocity was constant, it would have 0 acceleration. So the motion is accelerating downwards. Okay, so do you want to try and draw the resultant force diagram for question B? You can pause the video, and when you come back, we'll go through the work solution. Okay, so welcome back if you had a go. So for question B, you can see that the force pulling it upwards is equal to the force pulling it downwards. This means there will be no resultant vertical force. So we have our particle. The horizontal force, however, there is 10 pulling it to the right and 5 pulling it to the left. So there will be a net force of 5 newtons pulling it to the right. The motion of this particle then means it will be accelerating to the right. Okay, let's try question 2. In example 2, we've been asked to draw a force diagram to show all the forces acting in each situation. So for example A, we've got a light bulb hanging from a ceiling. So we'll start by drawing the ceiling, which is a horizontal surface here. Then we have a piece of rope or string connected to the light bulb, which I'll draw in yellow. So now the forces, well, you can imagine that we've got the weight of a light bulb pulling it downwards. So the force pulling it downwards is the weight. But because it's not moving downwards, there must be another force acting upwards. And this is the tension in the string holding the light bulb. So the two forces are the tension in the cable of a string and the weight of a light bulb pulling it downwards. Okay, so do you want to try and draw a force diagram for question B, for question C, and for question D? When you come back, we'll go through the work solution. So for question B, a cup lying at rest on a table. So we'll have the surface of a table. And because it's at rest, it means that the cup is in equilibrium, which means it's staying still. So we have no horizontal forces. We do, however, have the weight of a cup pushing it through the surface. And now we've got the normal reaction of the surface on the cup pulling it upwards. So this would be the normal reaction. Okay? So for part C, a cup at rest on a table but being pushed by a small horizontal force. So again, we've got a surface, a cup, and because it's being pushed by a small external force, we've got a compression force acting to the right, we'll call this compression. We could also have called it thrust. We have a force acting downwards, which is the weight of a cup. We have a normal reaction exerted by the table on the cup. And we've got friction acting in the opposite way to the compression. So you've got four forces. The weight and the normal reaction are equal, and the compression is greater than the friction. Okay? For question D, a horizontal ruler being used to bridge two books. So we can have our books here and here. We have the bridge between them. The weight of a ruler will be pulling it downwards, and this is our downwards force. And the normal reaction here and here will be acting on the ruler from the books. So the normal reaction here and here. Okay, let's try one more question. So in example 3, we're told that a plank is pulled vertically upwards at a constant velocity by 3 equally spaced ropes. And for question A, ignoring any air resistance, work out the tension in each rope. So here are your 3 ropes, equally spaced along this plank. And then for part B, the tension in each rope is reduced by 10 newtons. Describe the resultant motion of a plank. So do you want to try and work through question B yourself? You can pause the video, and when you come back, we'll go through the work solution. Okay, so welcome back if you had to go. So the important thing to think about here is that it's pulled at a constant velocity. This means that the acceleration is 0. The velocity is constant, so it's not changing. And because it's not changing, the force pulling it up by the 3 ropes must be equal to the downwards force of 360 newtons. So we can say that 3 lots of the tension in the rope, 3T, will be equal to 360 newtons. So T, dividing both by 3, T will be equal to 120 newtons. So the tension in each of these ropes is 120 newtons each. For part B, if the tension in each rope is reduced, how will this affect the resultant motion of a plank? Well, if the upwards tension is less, then the downward tension will not be greater. Then there will be a net downwards force. And we can calculate this as the upwards force is now 3 lots of 110 newtons, because we've taken 10 away. So this is 330 of an upwards force. The downwards force is still 360. So the net downward force will be 30 newtons. And this will cause the plank to accelerate downwards. Okay, so thank you very much for watching. I hope you found that useful. You can download the full lesson and worksheet on my website, mrmathematics.com. There's a link to the lesson in the description below. Thanks again, and take care.